on exam 3.
All right. And my last question is more of a conceptual question.
Yes.
Okay, so what we're doing right now, I wanted to see, like, do we think of this as us interacting with machines, or what would be the frame to put this in? I mean, is there a specific frame of mind that we want? Like, what kind of structures are we building?
You're building formal structures that define languages. And those languages have different characteristics. We've established that there are certain types of languages which we call regular languages, which can be defined in a variety of ways, all of which result in the same type of class of languages. We are now working with context-free grammars, and we will see that the languages generated by context-free grammars are exactly the languages that are accepted by a different type of automaton called a push-down automaton. We haven't gotten there yet, and that will be later, after the second exam. Okay. All right, so we have so far looked at context-free grammars, and we have established that we can eliminate epsilon productions. Which means we can basically, if we have an arbitrary context-free grammar G, we can get a new set of context-free productions, such that the language generated by that new set of productions is exactly the language generated by the old context-free grammar, possibly removing the epsilon if it was there. Because obviously when we eliminate epsilon productions, there's no way we can generate epsilon, but everything else can be generated. Now we're looking at unit productions. Unit productions are productions where a single variable goes to another single variable. So the right-hand side, the left-hand side is of course always a variable. The right-hand side is a string over the terminals and variables, and if that happens to be a single variable, then that is called a unit production. And we want to get rid of that too. We want to eliminate them, and if you understand how to eliminate epsilon productions, the concept is exactly the same. So you take if you have distinguished two different situations where the A goes to B is the only A production, in which case you simply replace every A in any right-hand side by B. Now, if that's not the case, if you have A goes to B, and you have also A goes to alpha, or more than one alpha, alpha 1, alpha 2, alpha 3, etc., then of course you have to systematically replace A either by B or not. So in order to get rid of the A goes to B, you replace every A in any right-hand side by A or by B. So if you replace it by A, it means you don't do anything. If you replace it by B, then of course that's an actual replacement. And that means, of course, if you have n different A's in one right-hand side, you will have 2 to the n different productions. So if you have C goes to A, B, A, then that would result in C goes to, well, if you don't replace any of the A's, then you leave it as it is. That's the one I skipped last time in the beginning. And so now you have to systematically replace each A by B. So you can replace the first A by B and leave everything else the same, or the second A by B and leave everything else the same, or the third A by B. So that replaces 1. And then you replace both 2. So let's say the first 2, B, A, B, and leave the last A, or you replace the first and the last A by B and leave the middle one alone, or you replace the second and the third and leave the first one alone. Come on. Let's see, B, A, I'm sorry, wrong. Come on. Yes. Misbehaving. Okay, so A, B, B, A. So that replaces 2 of those 3 A's by B and leaves 1 A alone. So we left the last one alone here, we left the middle one alone here, and wrong. This is not what it is. So what did we leave the first one alone. So this is A, B, B, B. Okay, so here we left the first one alone and replace the other 2 A's by B. And finally, we replace all 3 A's by B, which gives me B, A, B, B, B. So in that way, you're replacing every occurrence by the corresponding right-hand side, so in this case B, and then you can get rid of the A goes to B. Okay, so let's look at an example. S goes to A or SBS, and A goes to B or SAS, and B goes to S or AB. So let's eliminate B goes to S. So that means we're going to replace every occurrence of B by S, or not, because obviously there are 2 B productions, the unit production and one that isn't a unit production. So we have B goes to S, and so we get S goes to A, SBS, or A goes to B, or S. An SAS. So this B is replaced by, not replaced, I mean, replaced by B means we're not doing anything, or we replace it by S. And then we have B goes to, well, this is gone, so we have just AB, because we eliminated that. So, as you can see, this can get a little ugly, because we had 3 unit productions. We eliminated one, and we still have 3 unit productions, because that gave us another one. So let's look at the A goes to B. So that means we'll replace every A either by A or by B. So this is S goes to A, or B, or SBS. And then we have A goes to, well, we've eliminated the A goes to B, so we still have S, or SAS, and B goes to AB. So we still have 3. We eliminated now 2, but we still have 3 unit productions. So let's work with the A goes to S. So that means every S that we encounter has to replace either by, every A that we encounter has to be replaced either by A or by S. So we have S goes to A, we don't replace it, or S, or we have B, and then we have SBS. And then we have A goes to SAS, and B goes to AB. So, as you can see, we've eliminated now 1, 2, 3 unit productions, but we still have 3 unit productions. S goes to A, S goes to S, and S goes to B. Well, we can obviously get rid of the S goes to S because that doesn't contribute anything, so we don't really need that, but we still certainly have S goes to A and S goes to B. So we have, let's eliminate S goes to A. That means we're getting rid of that, so we have S goes to B and SBS. So here we have 2 S's, and that means we can either replace that S by S, meaning we're not doing anything with it, or replace it by A. So there are obviously 4. We have 1, then we have ABS, SBA, or ABA. Those 4. This is what we get from this S goes to SBS, those 4 productions. Then we have A goes to, well, SAS. We're not changing anything. Or we can change each of those S's to A's. So again, we have a similar situation. We're going to get 4. So SAS, AAS, SAA, and AAA. And then we have the B goes to AB. So we're down to 1 unit production, which is S goes to B. And in this case, we have to replace every S either by S or by B. So this is going to give us 4 for this, 2 for this, 2 for this, 4 for this, 2 for this, and 2 for this. So I'm not going to write all of them down. SBS, B, BS, SBB, and BBB. Well, then we have ABS and ABB. So this is this. Then we have SBA or BBA. And then we have, of course, ABA. And then we have A goes to, well, 4 of these, S, A, S, B, A, S, S, A, B, B, A, B, or A, S, or A, B from this one, and then we have S, A, or B, A, and A, and then we have B goes to A, B, and that then is the final result of eliminating all unit productions from that given grammar. So in contrast to an epsilon production, where you can have at most one epsilon production per variable, in this case you have seen that you can get more than the number of variables, unit productions. In this case we had 1, 2, 3 to begin with, and then we created another one, 4 and 5 and 6. So this one is of course not particularly useful. S goes to S, so we can immediately get rid of it, but we certainly had 1, 2, 3, 4, 5 unit productions.
Professor,
Yes.
I have a question. So I don't understand how the process, you just showed this process, but I don't understand what am I looking at to get the next step. So it looks like you're going down, right? You're working from S, and then you're working from A, and then you're
I
working from
did
B.
B goes to S. Okay, that's the first thing. So that means I have to troll for all B's. There's only one on the right-hand side. This is it. And so I replace that B, either leave it alone or replace it by S, which I did here. Okay, so that was the first step, to go from there to this. Everything else was the same. Then I eliminated A goes to B. So I'd have to troll for A. There is 1. This is that A. S goes to A, and that A then is going to be replaced, either leave it alone, don't do anything, or replace it by B, which is what I have here. Okay.
This is because that was nested, correct? So A goes
There's
to B
nothing
and B.
nested. I'm simply going to do A goes to B. I'm going to get rid of it. That's why it's missing here. Okay?
Okay, so A goes to B and B goes to S. So therefore, you could just say A to S. Is that what we're thinking about?
I do one unit production at a time. I do A goes to B. What I have to do is look for a B. Well, I'm sorry, look for an A. There is a single A here. That's the one I'm working. That A is either left unchanged or it is replaced by that B, which I'm doing here. So now I've eliminated A goes to B, which leaves me with this as a result of the replacement, plus the A goes to S, which I didn't do anything with, and A goes to S, and the B goes to AB. So that was going from eliminating the A goes to B, from this to that. And now I'm going to eliminate A goes to S, which means I'm looking for an A, which I have here, and I replace it either by leave it alone by A, or I replace it by S, which I did. S goes to A, or S goes to S. Well, S goes to S doesn't really make a whole lot of sense, so I can get rid of it. And so I have S goes to A, S goes to B, S goes to S, B, S, and I've eliminated A goes to S, which leaves me with A goes to SAB, SAS. And so I have S goes to A, S goes to B, S goes to SBS, A goes to SAS, and B goes to AB. And then I have to replace the S goes to A. So I'm looking for the S. I have here an S, two S's, two S's, so that gives me 4 for this, so which I have here. That S goes to B is unchanged, and then I have the S goes to SBS, 1, 2, 3, 4. And then I have the A goes to SAS, that gives me 4 more, 1, 2, 3, 4. And then the B goes to AB, and that stays unchanged. And finally, I get rid of the S goes to B. And so I'm going to do that. And so I have S goes to B. I get 4 from this. These are the 4.
Wait, 4 from where?
From this.
What are you pointing at? I'm sorry, I can't.
This one.
Okay, so that one gives out 4 different iterations that we had from earlier.
It gives, I'm sorry, this is it.
So that SBS can also be turned into, this is just the combination of the S's being replaced by B's.
Right. And then I get 2 from this.
And here we're trying to replace these at all?
No, I'm just going to go for the S again. And then I have this, which gives me those 2, and the ABA is the same. And then I do the same thing with this. So this is those 4. And then I have this 1, 2. This gives me 2. And then I have that, which gives me 2. And I have that. Okay, and so what I circled in blue is then the final answer, starting with this.
How do we know that that's the final answer? Another question.
Do you see any unit productions in here?
You know what? That's exactly the problem. Where do you define a unit production? Is a unit production just something pointing to something else? Because I'm seeing what I would consider to be.
This is a unit production. A variable goes to a single variable.
Okay, so if a variable on the next one right now, the answer, none of the variables will go to another variable.
Correct. So that's why we have eliminated all unit productions.
Okay, thank you.
All right. Okay, now what we need to do, we could have done that at the beginning, but now that you are involved in that elimination game, let's eliminate one other thing, useless symbols. Now, when is a symbol useless? There are 2 possibilities. And typically, I use symbol most of the time we're looking at variables, but as you will see in the example, they could be terminals too. So if we have a variable x, and it does not do this, it does not generate a word over the terminals, then x is useless. No w's that, well, shouldn't write it. No w such that a variable generates that w, and that's of course over the terminals. This is important, okay? Then x is useless. In other words, if we can't use x to generate something that is over the terminals only, then the x really doesn't do anything for us. So that's the first case. The second case is there is no derivation. S derives alpha y beta for y in union T. Then y is useless. The first case basically says we can't derive anything over the terminals only. The second case is I have to start with the starting symbol. If I don't have something that begins in the starting symbol and eventually derives a string that contains this y, if that doesn't exist, then that y obviously is no good. So in that case, y is as well useless. So how do we find out the first? Nothing can be derived from from x. Okay. So what we do is, obviously, the first thing we have to do is look. So we have a grammar. She is NTPS. And we look first for a production x derives a string over the terminals only. Now, that is always the starting point. So we'll write down all of our variables, S, A, B, C, and so on. And in the first step, the first generation, if you will, we mark those variables that satisfy this. So this is that first step. Now in the second step, we're going to look for x produces, these are all productions, okay? W, as well as an A that has already been found okay in the first step. And then we keep repeating that. So we're going to go for, this is several generations, okay? We'll first look at what can we derive directly. So obviously if we can't find any variable, not a single variable that generates in a production a string over the terminals only, then there is no hope. And now if we have, say, if we know that A is okay, A we may have, let's just look at an example. S goes to A, and A goes to epsilon or B, and B goes to C, A, B, and C goes to S, A, S. Okay, so let's look at this. we have S, A, B, C. And so in the first step, we look at what variables actually generate a string over the terminals only. Well, that happens to be A goes to epsilon. That's the only production where the right-hand side is a string over the terminals. So A is okay. Nobody else is. Okay? There is no other.
Professor, what does that mean in this situation?
That A produces a string over the terminals. That's what it means. So in the next step, then, we'll look at what can we do with that A, or possibly some other terminals. So obviously we can, A is already established to be okay. So now we have to look at what can we do with A. So we have S goes to AA. So since A is okay, and S goes to AA, S is now okay. All right? So that means S is from now on okay. Then
I'm sorry. Could I ask a quick question?
Sure.
If S were to go, say, to a B, would it be okay then?
No.
Okay, just wanted to check.
Because B doesn't have a tick mark.
Right, I thought so. I just want to make sure it had to be all of them. Okay. All right.
Okay. B doesn't have a tick.
I have a follow-up on his question.
Sure.
So does this mean, because A goes towards the terminal, and we derive that because A goes to epsilon?
A goes to epsilon means we have this situation.
Where and so that spans, where X is, I'm sorry, let me just, what does this situation mean? It says X goes to W, which spans over T being the terminal.
Consists only of terminals. Well, epsilon consists only of terminals. 0 terminals. There's no variable, in other words.
Oh, okay, I see. So that means that there's only terminals in there, and that's because it actually has an epsilon.
Correct. And then we have the next step is S goes to AA, which means the A is okay, and therefore now the S is also okay. Okay, and so now the next step is that the C is okay because the S is okay, and therefore the C is okay. All right, so that is that. And now what is the next step? Well, we have S, A, and C. What about B? Well, B is not okay because B goes to CAB. Well, C is okay, but B is not. Therefore, there's nothing. And that means this step 1, 2, 3. In step 4, we get exactly the same thing as in step 3, which means that this is it. So at that point, it terminates, because if we have the same identical column again, identical to the one before, we have no hope to expect anything further down. So this is it. Which means S is okay, A is okay, C is okay, but B is not. which means that B is a useless symbol. B does not generate anything over the terminals only. And that means that we get rid of this production and this production. So the result of that process is that we have S goes to A goes to epsilon, and C goes to SAS. And now, it is of course clear that we have an instance of the second case. There is no derivation from S to C. Okay? So you cannot find anything that gives you C somewhere. The way you do that is you look at a starting symbol, so that means S is okay. And then S gives you AA, so A is okay. And that's it. From A you get epsilon, and that's all there is to it. And so the result is that you're going to get S goes to AA, and A goes to epsilon. And that implies that useless symbols in this case are, well, the variable B, the variable C, and the terminal A. We started out with all of that, and we ended up with this.
Is there uselessness because they lead nowhere?
They don't generate anything that we're interested in. They have to generate something that is over the terminals, and they have to be reachable from the starting symbol.
Professor, what does it mean that the first box in to the right of S is unchecked? That doesn't have anything to do with the starting symbol?
You mean this one?
Yes.
It is unchecked because there is no S goes to a string over the terminals.
Oh, okay. So, yeah, okay. So it's only variables that it points to.
Only variables that actually do that. So the only variable to start out with is A goes to epsilon. That's the only variable that generates something over the terminals only, and therefore the A is checked and nothing else.
Okay, and so the S is valid because it points only to the A, which is valid.
S goes to AA. There could have been a C in between, for instance, a little c. That would be fine, but I didn't have it. But so it doesn't make any difference. The point is that now that A is okay, S becomes okay in the second step. And once S is okay, then in the third step, C becomes okay. And then when you do the same thing again, you're going to get back exactly the same. S, A, and C are all three okay, and B is not. Therefore, B is gone, and A goes to B is gone. And so that means, according to that first requirement, we got down to this SAC. And now the second requirement stipulates that, well, if we start off with S, because S is of course the starting symbol, then we have to be able to reach every single symbol. Well, the C cannot be reached. Neither can the little a be reached from S. And therefore, C goes to SAS is no good. And the only thing that's left then is S goes to A, and A goes to epsilon.
Okay, thank you for that.
Okay. All right. So now what we have is we can eliminate well, first we do useless symbols. That's basically just because we're lazy. Okay? If you could eliminate the useless symbols later, but if you can eliminate something that you don't really need, it will make the elimination of epsilon productions and unit productions easier. So I recommend you eliminate always the useless symbol first. I mean, if you look at this example, you'd have a unit production, you have an epsilon production, and that is what you would have to eliminate here. But once you've eliminated all useless symbols, you end up with this, and then obviously what you're going to get from that is that the language that you're going to get is going to generate nothing. Because clearly, if you look at this, S goes to AA and A goes to epsilon, that means S goes to epsilon. And in the context of what we're doing, namely that we cannot generate epsilon, and that's the only thing that this grammar generates, it follows then that the language that we get by applying the epsilon production elimination to this grammar is going to be the grammar that doesn't generate anything, which of course it should. That should be the answer, because this grammar generates only epsilon. So
Professor,
yes.
So I have a question on the word terminal. And in terms of a grammar, what does the terminal part of the equation do?
There is no terminal part. This is a terminal, which is basically the same thing as the input symbol. It's
Okay.
not a variable.
So it's the input.
Yes.
Thank you.
Okay, so first we eliminate useless symbols, then we eliminate epsilon productions, and then we eliminate unit productions. This is important. The first you can do anywhere, anytime you want to, the useless symbols, but you have to do the epsilon productions first. Get rid of them first, and then you get rid of the unit productions. The reason for that is that when you eliminate epsilon productions, you may generate new unit productions. And that, of course, would mean if you first eliminated unit productions and then you did the epsilon production elimination, you may have to do the elimination of unit productions again, because elimination of epsilon productions may generate new unit productions. If you first do the elimination of the epsilon productions, then when you eliminate the unit productions, obviously unit productions don't generate epsilon the elimination of unit productions doesn't generate epsilon productions. So if you do it in this order, you will end up with a grammar that has neither epsilon productions nor unit productions. Okay, so now we finally can do what all this is necessary for. Chomsky normal form. Chomsky normal form says that any given a context-free grammar G, there exists a context-free grammar G prime such that L of G prime is equal to L of G minus epsilon, and every production in G prime is of the form A goes to BC or A goes to little a. So in other words, all productions either are such that the right-hand side is exactly two variables or a single terminal. Now, if you contrast that with the regular grammar, well, the regular grammar was AB or A. So in that case, the difference here is that we have two variables. In the regular grammar, we had a terminal followed by a variable. In Chomsky normal form, we have two variables. Now, it should be fairly clear that this difference is very crucial between a terminal followed by a variable versus a variable followed by a variable. Because if this is correct, and we will see that in a minute, it's actually very simple. Most of the heavy lifting was already done when we did all that elimination of epsilon productions and unit productions. But obviously, this is a regular grammar, and it generates a regular language. On the other hand, if I'm given an arbitrary context-free grammar, for example, this one, then that generates obviously something that isn't necessarily regular. This one is obviously A to the n, B to the n. We've done that already, and that we've shown is not regular. So that shows you that this is actually a crucial difference. Two variables versus a terminal followed by a variable. That's the only difference between a regular grammar and a Chomsky normal form grammar. And just in case you're wondering, well, this Chomsky is actually the left-wing gadfly, Noam Chomsky, who came up with that about 45 years ago, 50 years ago.
What was the phrase you described him? Left-wing what?
Gadfly. Google Noam Chomsky and you will see.
Oh, I know.
He's a linguist. He actually is was heavily involved in formal language theory. Of course, he's not working on that anymore. He has progressed to other things, progressed rather deliberately chosen. So Anyway, yes, that
So,
Noam Chomsky.
Professor, so in this situation, for the one that you showed on the bottom, the main difference between that and a regular language is that this uh, deals with two languages.
No, it doesn't. It has two variables.
Okay, it has more than one variable, and that's what makes it a
No,
non-regular language.
now, why are you interpreting what I'm saying wrongly?
Right,
I
so,
said two, not more than one. I said two.
okay,
That's
so it
what
has,
is stipulated here. A goes to B, C. That means a variable followed by another variable. No more or no less.
mm-hmm,
Okay?
got it.
All right. Okay, so how do we get that? Well, this is actually not very complicated. Basically, we have A goes to alpha. This is a production in G. Now, the first thing we do is we eliminate. Use the symbols epsilon productions and unit productions. Okay, so now we go back to how does a general production look like? Well, because we've eliminated epsilon productions, the alpha can't be epsilon. Because we've eliminated unit productions, the alpha can't be a single variable. So we know alpha is not epsilon, and alpha is not a single variable. So there are now the following possibilities. Alpha could be a terminal, which is fine. This is one of the two forms that we are willing to accept. The second case could be that, well, alpha is at least of length 2. That's the only other possibility. Either alpha is a single terminal, or that alpha is at least of length 2. Now, if we have this, if alpha is of length at least 2, replace each terminal B by the variable xb, and xb generates B. Okay? That's sort of a formal trick that allows us to basically replace every terminal by a variable. And we do that only if the alpha is at least of length 2. So if we go with that production, with those two productions here, then we'll have S goes to XA SXB or XA XB. Remember, this is the productions that we had, ASB. Well, so we replace the A by XA, the B by XB, and we generate XA goes to little a, and XB goes to little b. This is simply to get things in a form where if we have a right-hand side that is at least of length 2, everything is only variables. Okay. So those two are already in the correct format. This one is in the correct format. Variable goes to 2 variables. This one is not. And so if we have an alpha that is of length at least 3, so we're slowly, this is sort of a salami tactic. We get rid of the epsilon. Alpha can't be epsilon because we eliminated epsilon productions. The alpha can't be a single variable because we eliminated unit productions. So what is left is, well, the alpha is a single terminal, which is fine. So we leave that one alone. And then the alpha has, if none of these apply, then the alpha has to be at least of length 2. Now, what we're going to do is, if there are terminals in that alpha, as there are, for instance, here, this is of length 2, this is of length 3, there is A, B, these are the two variable terminals we have, so we're going to replace them by variables, XA and XB, and so that's what we did here. And the other one is, of course, that we have the ASB. So we replace the A by XA, the B by XB. So we have XASXB. Now this is of length 3. And what we're going to do then is, if we have that alpha, say this is of length m, x1, x2 through xm, m greater or equal to 3, then we do replace this by s goes to x1, s1. And then s1 goes to x2, s2. S2 goes to x3, s3, and so on. We go to sm minus 2, which goes to xm minus, let's see, xm minus 3, sm minus 3, m minus 2, sm minus 2, and then sm minus 2 goes to xm minus 1, xm. This looks complicated, but it is actually completely trivial. You basically take, so let's just look at a simple example. S goes to A, B, C, D, E. So what are we going to do? We replace that by S goes to A, S1. Then S1 goes to B, S2. And S2 goes to C, S3. And now the only thing we have to pay attention is that the last two then are going to be generated by the last auxiliary. S3 goes to D. So you can easily see, you take the S3 and plug it in here, so you have CDE, then you take that S2 and plug it in here, so you then have BCDE, and then you finally plug in that S1 in here, so you have ABCDE, which is, of course, what you want. So that's what this does. And that gives you Chomsky normal form. That's the end of that. So, coming back to that example up here, so we have S goes to XA S1, and S1 goes to S xb, and then of course we have S goes to xa xb, and so that is what we get for the S productions, and then we have xa goes to A and xb goes to B, and that is the answer for the grammar that we started out with, namely this one. So this is now a Chomsky normal form. And basically this is sort of a zipper that you're doing. You start with the first, and then you simply use one up at a time until you get to the last two. Oops, no, we don't want that. The last two. Okay. And in this case, of course, it's 3, so you need only 1. So it's n minus 2. So in this case, you have 3, so that means you need 1. And if you had, say, S goes to ASB or CSD, or AB or CD, then you first, there are no unit productions, there are no epsilon productions, there are no useless symbols, so this is what you get to work with. And so you then replace S goes to XAS XB, XCS XD, XA XB, XC XD, and you need, of course, XA goes to A, XB goes to B, XC goes to C, and XD goes to D. This is just that subterfuge to get rid of terminals by replacing them systematically by variables. And then you have S goes to, well, XA S1. So we're working with this. And then S1 would go to SXB. And then you have the second one. S goes to XCSXD. So you have XC. S2, you simply continue numbering auxiliary variables. S2 goes to SXD. And then you have XAXB. That's, of course, fine. It's already in Chomsky normal form. And XCXD is also fine. And so you'd have this as a result. I'm sorry. Keep forgetting. You need this. All of that. Instead of that. So once you've eliminated useless symbols, which is of course just because we're lazy, epsilon productions, yes, we need that, and unit productions, yes, we need that, then the rest is fairly straightforward, almost unthinking. So that gives us Chomsky normal form. Well, there is a second type of normal form that we need to consider, which is Greibach normal form. This one was named after Sheila Greibach, one of the relatively few women in theoretical computer science, certainly early formal language theory. We're talking about 1960s. Greibach normal form basically says, given a context-free grammar G that exists, a context-free grammar G prime, such that L of G prime is L of G minus epsilon. Again, this is always, epsilon is being criminally discriminated against. So epsilon is always taken out. And each production in G prime is of the form A goes to B1, A goes to little a, B1, B2, Bm, m greater or equal to 0. So what that means is that we can transform that original grammar G into one where all productions have a right-hand side that starts with a terminal and then follows 0 or more variables. So you can have A goes to little a, or A goes to AB, or A goes to ABC, or A goes to ABCD, or so on and so forth. M greater or equal to 0. This is, of course, m is equal to 0. This is m is equal to 1, m is equal to 2, and so on and so forth. So again, this is somewhat reminiscent of what we had for regular grammars. In terms of what we have for Greibach normal form, we're basically looking at those first two. Okay, this is m is equal to 0, and this is m is equal to 1. And of course, in Greibach normal form, the m is unlimited. It could be 1, 2, 3, 0, 1, 2, 3, 4, 5, etc., and so on. So again, this is pretty close to regular languages, but of course it isn't a regular language because the context-free languages, which are the languages generated by context-free grammars, are much larger than the regular languages. And so if we just limit it to those first two cases, m is equal to 0 and m is equal to 1, we have exactly regular grammars. But given this statement, given a context-free grammar G that exists, a context-free grammar G prime that accepts essentially exactly the same as G, except for that empty word epsilon, and each production in that new grammar G prime that we constructed is of the form a variable produces a terminal followed by 0 or more variables. Now, in terms of the process of doing this, it basically means that if we have a derivation of a word W and the word W is of length n, then in each step we will generate exactly one terminal. So that means that the number of derivation steps of that word is exactly n, because in each derivation step we are going to get exactly a single terminal. And so if we have n terminals in that word W, then we will have n different derivation steps, each of which will yield a single terminal. So, I won't be able to show you all of that today, but what I can show you is left recursion. Left recursion is a situation where we have a variable a derives in, well, one or more steps. Oops. Star is 0 or more derivations. Plus is 1 or more derivations. So left recursion is the situation where you have a variable a that then generates something that starts with that variable. Now, that is quite undesirable, certainly in the case of parsing programs in a compiler, because basically you would get a situation where you have a variable a, and then that variable gives you that variable followed by something else. And so when you expand that variable again, you're going to get, it never terminates, which is probably not the kind of thing you want your compiler to do. So left recursion is undesirable. It is important that we concentrate on left recursion, because if you had simply recursion, well, that is something that you cannot avoid. Well, you can, but consequences would be fairly dire. So this would be recursion. Now, if you didn't have no recursion, what would that mean? There is no variable that will generate some stuff followed by that variable followed by some other stuff. If you had no recursion in a context-free grammar, what would that imply? Well, it implies that L of G would be finite. If you don't have recursion, you can really not generate a whole lot. It is crucial that there be recursion in order to have an infinite language. Without recursion, there's no infinite set, no infinite language. And if you think about it, obviously you want to have any programming language must be infinite. You don't want your compiler to tell you, well, gee, this program is too long, I'm not going to compile it. That's what finite means. So obviously, if you look at any programming language, then it is unlimited according to the way in which a programming language is defined. There is no upper limit on the length of the programs. Now, there may be a practical limit on the length, but it has nothing to do with the formal definition of the language. And so if you don't have recursion, you will end up with something that is finite, which basically means, for all practical purposes, useless. Not in the sense of useless symbols, but just of no great use, practical use. So when we say we don't like left recursion, and of course that's what this is leading up to, and by now you've probably figured out when I say we don't like something, then we eliminate it. We want to eliminate left recursion. Now, again, I repeat, we are not attempting to eliminate a recursion, because obviously if we were to do that, we'd be replacing an infinite language by a finite language, which is complete nonsense. But we can eliminate left recursion. And that is something that will have to wait a little, because if you recall, you have a miserable existence next week. You don't have class. I'm sure you're disappointed. Spring break. So we will resume that after spring break. I know you're very disappointed. Okay, any questions?
Professor, could we go over the slides slowly so that we can take pictures?
Sure. All right. Number 1. Number 2. Number 3. Number 4. I know you're all crestfallen about the lack of lectures next week. What a pity. Number 5. Number 6. Number 7. And number 8. Any other questions?
Oh, I have a question. As of now, how many questions out of the exercise set 2 are we able to answer?
All but the last one.
Okay, thanks.
Last one deals with Greiberg normal form, which we haven't solved yet. But everything else, 1, 2, and 3. And of course, in number 4, Greiberg normal form, you can obviously get rid of the epsilon productions and the unit productions. But the actual Greiberg normal form, you can't do that. Any other questions? Well, then I wish you a good spring break. Don't overdo it. Don't forget everything. And I will talk to you in 12 days.
All right, thanks,
Bye-bye.
Professor.
All right, thank you, Professor. Bye.